Hey everyone, welcome to our winter break update meeting. Um, so the point of this presentation is just to go over everything we did this semester. Um, I was planning on releasing this a couple of weeks ago, but I actually took a really long time to make. And then the past 2 days I've had like some issues with my laptop, but that's all fixed now. So I guess let's just get started here. So let me go to the next slide. So a quick overview of the presentation is just going over the recovery system, what that is, and our approach, and then going over the needs and constraint. Then we're going to go over the previous design, what it was, the drawbacks and the feedback we got from it, then the changes we made, and then that's going to take us into the last part, which is going to be over our current design, and then we're going to explain it, and I'm going to take a close look at all of the parts and the components we're using. We actually have a lot of components in the recovery system, so I'm just going to like run through them and just make sure that everything works and show all of you that it should work. I actually like cross-reference and read every single specification for like all the components to make sure that we're all compatible. But anyways, after that, we're gonna look at drawbacks and feedback, and then we're just gonna have like a section where we go over the final concerns about the design. Okay, so recovery system. So like I said at the beginning of the semester, the goal of our recovery system is to retrieve the rocket in a capable flight condition. So that pretty much means retrieving the whole rocket. You can't just like recover part of the rocket, it has to be all of the rocket. And that means minimal to no damage. And since we are competing in the Spaceport America Cup, that means that we also need to abide by the IREC recovery design guidelines. So our approach, or the way that I had planned it, was to follow these different 4 sections. So started off with brainstorming, then research, prototype, and final build. I think overall we've done a pretty good job with the brainstorming and research. It wasn't always kept really structured just because there was a lot of things to do, and then with school and the new members, it was just really hard to um, be on top of it. But I think in general, overall, we did do a lot of brainstorming and research during the semester. Documentation and communication. At the beginning, I feel like we did a pretty good job with documentation and explaining our reasoning for major decisions. But as the semester went along, it became kind of difficult to keep it up. And I feel like especially after the PDR, there was just so many decisions to make, and it became really hard to stay up to date with everything that was going on because we were making a lot of changes. And that's something that I think I could have done a better job at, just keeping the members more involved a little bit, um, especially after the PDR. Uh, Unfortunately, there was just like so much that we had to decide, and it was hard. Um, so that's something that I'm going to try to do a better job at going forward. But I think we did a pretty good job at just thinking about our design and doing research and finding everything that we could. And moving on now to the IREG recovery design guideline, there's 25 for recovery and avionics. They're like in the same section. 18 that apply to CNET. There's some that are for modified COTS and other ones that are for SRAD. And out of those 18, 12 only apply directly to recovery, our recovery. Um, the other 6 apply to what we consider avionics. So I have them here. If they're green, that means they apply to us. If they are purple, that means they apply to avionics. And if they are like this magenta purple. That means that would be like modified COTS and SRAD, so we don't even have to worry about those. But first one, I'm just gonna run through these real quick. This is just to remind everybody of what we're supposed to do. And as I go through this presentation, just keep these in mind and make sure that we're actually meeting them. So the first one is dual vent parachute and parafoil recovery. Yes, it's pretty self-explanatory. It just means we need to have 2 parachutes because we're flying above 1,500 feet. Initial deployment event, that just means deploying the drogue near apogee main deployment. That one, you just need to be 1,500 feet away from ground level or lower to deploy the main. Ejection gas protection, self-explanatory. Parachute swivel links, self-explanatory. Parachute coloration and markings, just having different color parachutes so you can identify if like the drogue or the main has deployed. Non-parachute, that doesn't apply to us. Redundant electronics, that kind of has to do with us, but it's more on the avionics side. A redundant COTS recovery electronic, more of avionics. SRAD pressure vessel testing, not us. SRAD recovery electronics, not us. Safety critical wiring for recovery system and air start motors. That's more of avionics, but we're not doing that this year, so it kind of doesn't apply. Cable management, just making sure that you have secure connections, secure wiring connections. Oh, sorry. Yeah, well, still kind of self-explanatory. Recovery system testing, self-explanatory. Ground test demonstration, self-explanatory. Optional flight tests, self-explanatory. Store energy devices. That one has to do with us, but also has to do with avionics. That just means that we need 2 different events for the ejection mechanisms to go off. So that means like having like something like an arm switch. That would be one event. And then the second event could be the flight computer telling your ejection system to go off. So that's what that means, which we are doing. Arming device access, that's avionics, arming device location, also avionics. And then the rest are for SRAD. So we don't have to worry about those. So overall, I would say that it's kind of straightforward what we have to do with our recovery system. Okay, so the components, we have U-bolts, quick links, swivels, cords, parachutes, deployment bag, fire protection, tender descenders, your primary ejection system, your secondary ejection system, and cables. Some of the main factors to consider, these are not all of them. I just think these are some of the important ones, but price, you want to minimize your price. Strength for that is basically that's dictated by your snatch force. Weight, you want to reduce your weight. Size and volume, you also want to reduce that. Performance, you want to maximize it. And complexity, you want to make things as simple as possible. So for the strength, for a lot of the components we're choosing, the strength is going to be based on the snatch force, which is the force exerted by the deceleration due to the deployment of the parachutes. So we did make a calculator this semester, which I'm really proud of that calculator. I think that it taught us a lot and it's been really useful. But anyways, there's also Dom's recovery calculator that he made, I think like 2 years ago. And then there's also Randy's recovery calculator. That one I have not linked to because I don't know if he's cool with us just like sharing it online. So I have not included the link for that. Our current snatch force or our load is expected to be between 130 to 170 pounds. And I'll talk more about why it's like not like a set number and more like a range. And then for all of our components, we chose a minimum strength of 1,000 pounds, and that gives us over a 5 safety rating or safety factor, sorry. So we should be pretty good. And then here in the figure, you can see what it is for the drogue. It's 84 pounds and 162 for the main. Now, size and volume, most of the bulk that we're going to take up is due to the parachutes and the cords. And therefore, one of the main things we can do to reduce the volume is making sure that we minimize the size of our parachutes and still meet our descent rate constraint, and also making sure that the cords are as small as possible while also making sure they can withstand the snatch force. Performance, that varies more between components, but in general, for something like for the ejection systems, you want to choose something that will work reliably, especially at 30K, since we're going up that high. For the parachutes, yeah, I kind of already mentioned that. And same thing for the cords. Complexity, overall, reducing the amounts of failure points. For the ejection system, that means choosing a system that has fewer parts and something that is easy to assemble, because I feel like assembly is one of those things that you want to minimize, because the more assembly you have to do, the greater the number of events that can go wrong, that can lead you or that can lead the system to fail. And recovery configuration, reducing the number of events in which components can fail to deploy due to various reasons. Yes, so there is like just the nature of recovery, there is a lot of failure points, but you want to minimize that. And we'll see that when we go over like our initial design and then we go to our current design. You'll see what I mean. So previous design. So this is what we had for the PDR. This was like our initial completed recovery configuration. And it's a single bay dual deployment configuration using the similar redundancy to eject the airframe at apogee and deploy the drogue. And then to deploy the main parachute, we would use tender descenders. That's still the case, but the way that the cords and other components are arranged is a little different. And I think the biggest thing about this design and the one we have right now is that the way that we had this one here, the nose cone is connected right under the quick link with the drogue. And then you have the tender descender here, the main over here. So in this configuration here, the main is in the bag when the drogue deploys. And then whenever you do want to deploy your main parachute, the tender descenders would go off, which would cut this connection here. And then all that tension from the drogue would get redirected through the next shortest cord, which would be this blue one here. And then this would pull on the bag for the main parachute, and then that would deploy the main parachute. And then this black cord here is the longest, and the point of this cord over here would be to keep everything together once the main deploys. So since the drogue and the nose cone are pretty much connected here, whenever we deployed our main, one of the concerns was that we didn't want the drogue to sit above the main parachute, because let's say we have this here, and then the drogue and nose cone is still connected with these cords here. But now let's say it was all the way over here above the main. We thought that was not a good idea just because it could get tangled. So our goal was to have this configuration instead, where the nose cone and the drogue is sitting under the main and the airframe. And the only way we could do that was by messing around with the parachutes. For the drogue, this meant falling within the descent rate of the drogue, which is 75 to 150 feet per second. In this configuration here, but then when we deployed the main, we wanted this to fall faster than the airframe and the main parachute. And this is what this figure shows here. So this 16.85 feet per second, that would be how fast the drogue and the nose cone would be falling. And then the 14.78 would be the main and the airframe. That's how fast that would fall. But I think I'm getting a little bit ahead of myself here. But yes, this would work. But one of the downsides of using these parachutes, I guess, was that whenever we were in the drogue configuration here, so it's just a drogue, we would be falling at 140 feet per second. And that's really fast. That's over 100 miles an hour. So during the PDR, we were advised that that was too fast. We should probably slow down a bit. And then similarly, the downside with this configuration here was that we would be falling too slow. We would be falling at 14.78 feet per second, which was just too slow, and it would take forever for us to get the rocket to hit the ground. But the justifications for this design were single bay, and that just meant reducing the amount of hardware and the amount of ejection events to occur to deploy the parachutes. And then, of course, our parachutes, they still were within the allowable range. It was just not optimized. And then the cords, they met the snatch force, which I'll talk about in a bit. But I guess more specifics about the design. The primary ejection system would be the smokeless powder system, which would be something like this. It's simple and familiar and should work at high altitudes. Randy has flown with it before, so I think there's a good amount of validity behind that. And then the secondary ejection system was the Raptor CO2 system. It's dissimilar redundancy. They're completely different methods of achieving ejection. So that's something that we believe to be really important. And it requires more assembly, but should have improved performance at high altitudes. For the main deployment, we had two L3 tender descenders, which are these really big tender descenders. I think these are rated for like 6,000 pounds of force. Our drogue was a 2 feet in diameter parachute with a coefficient of drag 1.6, and our descent rate was 140 feet per second. And then our main was 10 feet in diameter, a coefficient of drag 2.2, and a descent rate of 16 feet per second, which is wrong. Should actually say 14.78. Moving on here for the cords, we had 3 different types of cords. We had rated Kevlar, rated for 500 pounds, and that one was just to have this connection here to the nose cone, to the rest of the configuration, I guess, and that would experience no load. It would just hold the nose cone. The next one was the one rated for 900 pounds, the 3/8 nylon webbing. And I think that one was meant for the drogue here, like this red one here, since the snatch force for this was 8 pounds, I believe. And then finally, this really, really thick cord, this one here, that's rated for 4,200 pounds. That one was meant to carry the snatch force of the main. So this blue one here. And at the time, with the calculator, we had the wrong formula for the snatch force, and it didn't take into account the time for the parachute to deploy. So we were getting really high values for the snatch force. We got 3,300 pounds. And in turn, that meant that we had to pick components that could withstand all that load. And what that meant was bulkier, stronger components that also cost more money. And then for the connections, you can see some quick links rated for 3,500 pounds. Same thing for the swivel. It's a U-bolt rated for 10,000 pounds, which, by the way, thank you, Frankie, for buying that U-bolt. We're still going to use it. And the most important thing about this design was that the snatch force was really, really wrong. And I would say it was not optimized at all, or it was not as optimized as we could have done. Um, and that takes us to our drawbacks. So trying to achieve that configuration where the nose cone and the drogue would have to sit above the main and the airframe. That meant that we had to mess around with the descent range a lot, and our parachutes were kind of not optimized very well. This takes us to this point over here. The main parachutes and the cords took up a considerable volume. Again, that was because our snatch force was wrong. So we needed these really strong components that were bigger. And our cost. At the time for this design, the cost of the recovery system was around $1,500. The parachute, the main one here, this parachute itself costs like $625. It was crazy. And the feedback we received for this design was that our snatch force was way too high. Like I said, we used the wrong formula. The cord lengths, some of the lengths were too short. And the feedback we got was that you want to use at least 1 times the length of the rocket for the cord that connects the drogue to the airframe. And same thing for the main parachute. You want to use a cord that's at least 1 times the length of the rocket. For the descent rates, they gave us this guideline that we want to be between 120 to 140. Randy thought that 140 feet per second was okay, but Dom thought that it was too fast. So I say if we have to, I think 140 feet per second should be okay, but if we can avoid going that fast, we should. And then our main descent rate should be between 20 to 25 feet per second. For reference, Oberon's was 22 feet per second. So then here we go into the changes we made. For the cords, we actually looked at all the possible Kevlar cords that we could find. I forgot to add this to the last slide, but one of the feedback we got was to use Kevlar cords instead of any other material, because Kevlar is really, really strong and it's really light. So we made this sheet over here where we kind of found all the different websites where we could get Kevlar from. And then from that, based on the price and how big, the volume, the thickness and all that, we narrowed down our decision. For this second iteration here, we had chosen the purple ones here from Juan Bat Hawk, but then later we changed to the ones from Apogee Components. Now the core lengths, we adjusted the core lengths to be at least 1 times the length of the rocket. And this picture here just shows what we changed the lengths to. So it's the same lengths as in this one here. It's just, or it's the same configurations. It's just, sorry, the lengths of the cords are a little different. And for this one here, we have 45 feet of cord in total. And then the snatch force, we went back and we fixed that. This is the formula that we had for the PDR, which was wrong. And then this is the formula that we should have used, which is a little bit more complicated, but it does take the deployment time of the parachute into account. And we fixed the calculator. And what we did was, instead of taking the predicted weight of Zenith, we used a worst case scenario, because the higher your weight is, the higher your snatch force. So that's what we did. And that's why we kind of have a range of what the snatch force could be. if we use the weight that we have projected for Zenith, we get a value closer to 130 pounds. If we use a worst case scenario, we get closer to 160 to like 170 pounds. And based on this here, it's 100 and, I don't know, let's just say it's 170 pounds. We could reevaluate a lot of the components. They did not have to be so strong now. Like that's why we went with 1,000 pounds. As before, when we had 3,000 pounds, we needed all of our components basically to be able to withstand 3,000 pounds of force. And then some of the other things we changed, we went from the L3 tender descenders, which are rated for like 6,000 pounds, to the L2 tender descenders, which are rated for 2,000 pounds. And same thing with quick links and swivels. And by the way, these are the parachutes that we looked at here. You can see they have different coefficients of drag as well as different diameters. And you can see the different descent rates here. These are the main parachutes, 24, 26, 20, 17, 24. So we were aiming something around 25 feet per second. And we wanted to reduce the size of the parachute. So if we could go with 7 feet instead of 10 feet, that would be great because it would take up less volume, and also try and reduce cost. And we ended up settling with the Fruity Chutes. And I'll talk more about why we did in a bit, but we still had the same configuration here. Up to this point, it was this exact same thing. It's just that our snatch force value had changed and we had pretty much changed all the components, but the configuration of the recovery system was still the same. So the drawbacks with the second iteration was that the design still relied with messing with the descent rates to have that configuration. Our drogue was still too fast and our main was still too slow because we still had the same parachutes. We still had these parachutes here at that time. It's just that our snatch force was lower, but the parachutes were still the same. Yes, so I'll take back what I said. I'm sorry, I thought we had already picked different parachutes by this point, but apparently not. That was after the second iteration. It's just this screenshot is like the current calculator and what it looks like. So sorry about that. Let's see. Yes, and our price was still a big factor. Now we were looking at around $1,100. So there was still room to optimize and make these things a little better. And at this point, the sub-team leads had a meeting with Randy. And Randy gave us a lot of feedback in that meeting, and this is what led us to our current design. But one of the things he said was that instead of having this configuration here, where the nose cone is attached to the drogue here, he suggested giving the nose cone its own cord. So instead of being attached here, it would be attached directly to the U-bolt on top of the bulkhead. Let's see here. And then he suggested looking at the parachutes from Fruity Chutes and take advantage of the included link that they have on top. And I'll show what that means in a bit. And then he also suggested using Kevlar from Apogee components. Since he had used them before, they pack light and they're kind of inexpensive. So this is what I meant by using the chutes with the link on top from Fruity Chutes. So those parachutes include a link on top of the parachute so you can connect other things to it. And what this would allow us to do is to simplify our design significantly by taking advantage of this. So this is what it would look like with the drogue. We would just deploy the drogue over here, and then the nose cone has its own code over here. One of my concerns that I brought up to Randy of doing this is that you will have to run a cord basically from the U-bolt over here, and whenever it's packed inside the nose cone before anything deploys, is that you would have this cord that would be running through all of those components to the top of the nose cone. And Randy's justification for doing this is that having this here is still a lesser risk than having the nose cone and the drogue the way we did, where you run into the possibility of everything getting tangled when the main deploys. By doing this, you eliminate that completely. And whenever you do eject, the nose cone, since it has its own cord and is 15 feet long, not 20, this is wrong, should say 15. And this one should be 15. I forgot to update the picture. But since it has so much cord, as soon as you eject, this cord is just gonna go out in its own way and it's gonna get out the way. But anyhow, the drogue will deploy. Then you have the tender descenders here, and then you have the lines for the main parachute. Now, when it's time to deploy the main, the tender descenders will go off here. All the tension from the drogue will get redirected, and it will pull on the main parachute bag. The main parachute will get pulled out, and because there is that link on top over here, we can have this here. And this looks way simpler and safer than what we had before. Sorry, that was my little brother saying good night. But yes, this is what it would look like. And I like this better because people do it all the time. You can see this picture here that's been done before. The previous design we had, it was complicated because we had to mess around with the descent rates a lot. And as you can see, it looks more complicated. So overall, it's more optimized and it's significantly less complex. Moving on here, the drogue and the ejection systems, those stay the same. The main deployment, we had the L2 tender descenders now. The drogue, we changed the parachutes out now because we didn't have to worry about the relative descent rates. So now we had a 2.5 feet diameter drogue with a coefficient of drag of 1.55, and we had a descent rate of 133 feet per second. It's small size and excellent performance, and it's within the range that we were aiming for. The main is 7 feet in diameter, coefficient of drag 2.2, descent rate of 25 feet per second, and it's small and excellent performance, and it's within our goal as well. And you can see here, this is the main here. It includes a 3,000 pound swivel, which is more than okay since our snatch force is only going to be like 170 pounds. It's pretty light. And then I remember this number here, 3.9 inches in diameter whenever you fold it, and 8.8 inches in length for a total packing volume of 105 inches cubed. See the coefficient of drag here. And then this is our drogue here. You can see the coefficient of drag. This one includes a 1,000 pound swivel, which is more than okay as well, because I think our snatch force for the drogue is like 80 pounds. And then you can see the weight here, the packing volume kind of doesn't matter as much, but it's here anyways. And then let's move on here. So here is the part where I said I was going to go into detail into all the components to show everyone. and get everyone's validation that this all checks out. But the cords here, the cords are from Apogee Components, as Randy suggested. We're going with a 300-pound Kevlar for the nose cone line. So that would be this one here. This one doesn't need to be strong at all because it's just meant to keep the nose cone attached and out of the way whenever we eject. And then the other cord is the 1,500-pound, and that would be used for everything else. So you can see here, this is a 300-pound one. It has a diameter of 0.1 inches. And then for the 1,500-pound one, it has a diameter of 0.23 inches, which is really, really good. And it's really light. So these cords over here, I think they do a significantly better job at reducing our volume and the bulk. And they should be pretty easy to fold. The quick links here, these are the ones we're going for are rated for 1,700 pounds, as you can see here. It has an opening of 0.38 inches, which is greater than the core diameter. The biggest one here is 0.23, and it should also be compatible with the thickness of the U-bolts here, as well as the swivels here. But yeah, the U-bolt you can see is 5/16 inches thick, and then the opening is 0.38. 5/16, that should be, I think is, let me see if I can find my calculator. I know it works, I just, yeah, it's 0.31 inches, and then this one's 0.38, so it should work. The U-bolt is rated for 10,000 pounds, which is more than capable of withstanding the snatch force. The swivels, the drogue and the main include swivels, so we don't really need to purchase any. These are rated for 3,000 pounds, and is just in case. I don't think we're going to be buying any swivel, especially since we have the ones from Oberon anyways. And I guess another thing about the tender descenders is that they do include the quick links. So we don't need to buy a bunch of quick links, we only need to buy a few. Nomex blanket, this one is the one that we found. We have one from Oberon, so we're not going to buy a new one. We're just going to reuse that. But in the bill of materials, I've included the link for like every component we would need just in case. But for something like this, we're not going to buy a new one. For the deployment bag, we are going to buy a new one because we have one from Oberon, but that one is for a 10-foot parachute. But anyhow, the packing diameter of our main parachute, like I said earlier, is 3.9 inches. And the deployment bag, there's two different sizes. There's a 5.5 and 6-inch one, and there's a 4-inch one. And this one here, you can see is intended for 4 inches by 12 inches long for parachutes up to 117. The one we have is 4 inches and 3.9 inches in diameter, and it's 8 inches long. So this one would work better. This one, theoretically, it would work. It's just not optimized for our 7-foot main parachute. So we are going to go with this one here. So the drawbacks of our system, I think one of them is that we are using CO2, and this might not necessarily be a drawback. It's just something that we have to think about. And that is that we are unfamiliar with CO2 system, and they require, I would say, some tedious assembly compared to how relatively easy it is to assemble the powder systems. And kind of the same thing with tender descenders. I don't think anybody has messed around with them. So we're going to be the first ones to do that. And then for feedback for this design, that's you guys. That's all of you. Please, if you have any feedback about our design here, this is like the moment to let me know. This is the time to let me know. I hope that everybody like sends me a message and like at least tell me, hey, I think everything looks good and it checks out. But if you think that if you see something wrong, I think you should definitely let me know before we purchase anything. But I guess final concerns with our system. The first one is the smokeless powder charges. Um, they are still unavailable. So we have to talk to Randy to see if he can get some for us or to see if we can recreate them. I hope that Randy can uh, get us like in contact with somebody who has them, because if we have to recreate it, that's gonna take a little bit more work and more testing. Um, but whatever the case may be, we'll figure it out. And then for the Raptor and the CD3 CO2 kits, we still have not decided which one we're going to use, and what criteria we're going to use to decide which one we're going to use. I think this is kind of solved though. I know that Dominic, he is a alumni who was in the team. He was the same person who made the calculator that I showed earlier, but he was around when they were messing around with both of those CO2 kits. So I'm just going to ask him which one he prefers and why. And I'll show him like the parts we have, mini cartridges, all that. And based on what he says, I think we should go with whichever one he suggests. And then the recovery base size. So we don't know exactly how much volume we're going to take up. So it's hard to give out an estimate to structures or analysis about how big we want our recovery bay to be. We did try to get an estimate using Oberon's cords, but Oberon's cords are significantly bigger and the parachutes from Oberon are different sizes. So I don't think it was a good estimate of how much volume we are going to need. And then tender descenders, we kind of had to figure out how they're gonna go off. Are we gonna have them go off at the same time? Is there gonna be a delay between the primary and the secondary one? That's a smaller detail, but it's still something that I think we need to figure out. Again, if you have any questions about the recovery design, please let me know. I thought it was going to take longer to go over everything, but surprisingly, that didn't take long. But if you need me to explain something, please let me know. And thank you to everyone for putting in time this semester, putting in the time this semester. I had fun and I learned a lot. I learned so much this semester, and I hope all of you did learn something. I'm excited for the semester that's coming up. I feel like we're going to be doing a lot of testing and just like getting to see the parts that we've been designing for months now. Is going to be really exciting. So these are the resources here. This is kind of like a list of everything we did this semester. If you want to look at all the parts we're using, go to the bill of materials. It has the link to all the components and some notes about them as well. The calculator is right here as well. The consolidated weights, that was our way of estimating how much Cena is going to weigh, but I don't think it's up to date. And then we have our trade studies, some other documents, a progress report, and the IREG design guidelines. So yeah, if you have any questions, if you have any concerns about our design, please let me know. I'm going to start filling out the order forms, but I'm going to wait until I get the validation from the recovery members before I do that. So thank you all for watching, and thank you for putting in the time this semester. Goodbye, I guess.